The next speaker is George Kokes, who's been chairman of the department that kept Keith Hall under constraint for the last years. And he's going to talk about the propylene oxidation.
Thanks, Bob. Actually, when I was asked to participate, which is my great pleasure in this symposium, I felt that I had a different obligation probably to Keith and some of the rest of you. It's already been pointed out that Keith has subtle influences on most of the catalytic community. He insists in subtle ways on how things should be done. But since he and I share the same floor in the chemistry department, his suggestions aren't so subtle. In my case, he sits on my students' examining committees. They have to turn to him for assistance and help. And so in many ways, I thought what I probably should do is, well, I guess what I really felt like, I almost felt like a student in some ways. I felt obligated that I have to present what Keith has taught me over the years. My association with Keith goes back, I guess, to about 1964, I think, when I joined Gulf. The first time I really had a chance to meet and get to know Keith. And so we worked very closely over the last 13, 14 years at the University of Wisconsin in Milwaukee. We've traveled together. I've heard we served on committees together, we run workshops together. And I think one thing that everyone in the catalytic community has to recognize and show a certain sense of appreciation for Keith is that he has committed himself, he has dedicated himself to the advancement of catalytic science. And I think that's important because too often people take the advancement of the discipline fairly simply, and since, as we all know, there's a certain amount of politics and how funding is distributed, it's important to have people like Keith Hall moving forward, stepping forward at the appropriate time, and giving his position on what's important to catalysis. And I do want to acknowledge that, in fact, today, I think it's something all of us ought to appreciate. So, what I've learned from Keith in the past 20 years, I think probably the one thing that stands out in my mind is that Keith has continually insisted that catalysis is a chemical phenomenon and it should be explained in chemical terms. I've heard Keith's arguments, the importance of, or the lack of importance of spectroscopic techniques. I think he's tried to impress upon many of us that they're important from a complementary sense, but we need to recognize that they should explain the chemistry as opposed to being studied in its own end. So what I've tried to do is sort of summarize a lot of the work we've done over the years, a lot of it with Keith's subtle influence, and try to hopefully show that this is the kind of approach I think Keith has tried to advocate over his career in catalysis. Really, the use of tracers, the use of model compounds, the use of spectroscopic techniques to help understand. And what happened? Is this the wrong button?
There's two buttons up there.
What's this connected? Oops. This one connects in the room next door, probably. Somebody's having trouble with their slides over there. Looks like, can somebody just turn that a little bit, or it will be slightly off screen. I wanted to use this as an illustration, I guess, in what I said about Keith's philosophy of catalysis. It really is a kinetic chemical effect, and it ties back into the whole general concept of oxidation. I pulled this out of a book by Merck and Hahn in 1932. They indicated that, as it's quoted there, a number of patents have been issued claiming the production of valuable oxygenated hydrocarbon products it may be concluded, however, that no process has been evolved for successful commercial exploitation. About that time, Hoover discovered catalytic cracking, and then a lot of work went into trying to take the light products and convert them to something useful. And of course, if you add an oxygen atom, it would become a reactive intermediate. Well, again, just to illustrate, try to drive home the point Keith has tried to make, this is just what happens in the passing propylene and oxygen through a blank tube, a glass tube, and you get a whole host of products. The red line is the propylene, the one I'm going to talk about. Well, I guess the point here is that a catalyst can affect the product distribution by controlling the kinetics. The selectivity is dependent upon the kinetics of the process. So the model reaction we've been studying is this oxidation of propylene to acrolein, and it turns out that this reaction, as Keith has tried to advocate, explains a whole host of other reactions involving hydrocarbons that have allylic hydrogens. And I'm not going to take the time to go through all the history on it, but I think at this point in time it's pretty well established that this reaction occurs via an allylic hydrogen removal, and so any compound that has an allylic hydrogen is susceptible to attack at the allylic position and either ends up as a conjugated diene or an aldehyde if that's possible. Well, one of the points, I guess, again, I'm trying to reflect on what Keith has pointed out, is that in a model reaction, it ought to answer certain specific questions about the reaction, the chemical aspects of the reaction. So a model reaction in a case of hydrocarbon oxidation seems to at least have to address the questions: how is a hydrocarbon activated? What type of active oxygen species are there? And then, of course, the question of catalyst structure, active sites, and what have you. Well, I think that workers throughout the past 20, 30 years have addressed these questions in a hydrocarbon oxidation, and it has, in fact, fulfilled the test of a model reaction. Well, let me just, for those of you who aren't familiar with the area, going back to that first slide, which indicated fairly strong pessimism with regard to production of oxygen-containing intermediates in the 30s, surprisingly, I guess it wasn't quite as I intended. I suspect, like some of you last night, the tutorial on superconductivity. I don't think this created quite the excitement that superconductivity did, but it did have, I think, a fairly significant impact on the chemical industry. 1948, the Shell Oil Company found that copper oxide was a possible catalyst that would produce acrolein in fairly good yield. And then in very rapid succession, not again quite as rapid as the superconductivity events, but I think from the standpoint of catalysis over about a 30-year period, and I think at this point the reaction is fairly well understood. The catalyst composition is fairly well understood, and how they work are fairly well understood, and the chance for major changes, I would suggest at this point, or major breakthroughs are fairly limited. And I think this is a good example of how an area has developed rapidly, and a lot of science has been understood in the process. Well, turns out the major catalysts in the oxidation used today are based on multi-component systems. Sohio has been active. It turns out a wide variety of Japanese companies. It's also a testimony to the comments we've heard in the last few days about competitiveness with Japan. Basically, these catalysts are based on bismuth, molybdenum, and iron, or on iron antimony systems, or really on molybdates or antimony-based catalysts. Well, the catalysts we've studied have been bismuth molybdates, uranium antimony, iron antimony, tin antimony. From all the work that's been done, it's really probably safe to say you can explain or understand this system by assuming that it's a redox system, one that was proposed for aromatic oxidation some years ago in the 50s. First reaction is the reduction of the metal oxide by the hydrocarbon, and then the reoxidation of the metal oxide by the gas phase oxygen. Through the years, it's also been pretty well established. There are multiple sites on these catalysts. I've looked at, and other people have looked at, one site responsible for the hydrocarbon activation, another site for the oxygen uptake. In other words, there's an oxygen inlet site, a hydrocarbon oxidation site, and also our activation site and oxygen outlet site. Well, isotopic tracers, one of the used techniques Keith has advocated over the years. And the isotopic tracers we have used, and again, I'm not going, most of this has been published, just to summarize, the tracers we've used have involved propylene with the deuterium atoms on the methyl group, and then the propylene with the deuterium atom on the vinyl group. Turns out those species or molecules are useful in the sense that the allylic intermediate that's formed is the same from each compound. However, the one on the left will allow you to study primary isotope effects, whereas the one on the right, of course, would not exhibit primary isotope effects. So you get some idea about the rate limiting step. However, you can also study subsequent carbon-hydrogen bond breaking steps after the allylic intermediates form. So, for example, if you start with the molecule on the right, you get the allylic intermediate. However, if there's this energetic step involved in removing another carbon hydrogen or a carbon deuterium, you will see a distribution in the acrolein that's not 50-50. In fact, you would see a higher proportion of this compound, the D2, I would call, forget this one, over that one. And so those isotopically labeled compounds are useful in trying to probe the subtle differences in the product's formation, the scheme to the product formation. There it is. I'm sorry for this. I tried to get a copy of the table, and I see they do it out of the preprint. It's in the preprint. But I just want to summarize what's been found, that with the bismuth molybdate system, or the molybdate system in general, you see a predominance of the D2 product over the D1 product, indicating that pathway, which or a process that involves removing a second hydrogen after the allylic intermediate is formed, is energetically involved. It is a slow step. However, the antimonate system, this product distribution is 50-50, indicating that once the allylic intermediate is formed, the subsequent process is fast. Well, let's just go back to this dual site mechanism again. So, from the isotopic tracer work, and like I say, there's a whole host of publications in this area by a variety of workers. The key point is that the propylene activation, the first question for a model reaction, how is the hydrocarbon activated? It's pretty well established that propylene is activated via an abstraction of an allylic intermediate, an allylic hydrogen to form an allylic intermediate. There may or may not be subsequent energetically important steps after the allylic intermediate is formed, but that's the key step in the hydrocarbon activation. Now let's turn to the oxygen. The key question in terms of oxygen is what type of oxygen is involved. Well, again, I think the workers in the area have shown that you don't want absorbed oxygen, since the original concept was in a redox system, you really are utilizing the oxygen of the catalyst itself. So the way we've tried to compare one catalyst with the other is to assume that all of the oxygen in the catalyst is active. So first approximation, of course, if it's not, this affects how in a flow system the amount of oxygen 18 showing up in the products would come out as a function of time. Well, this is just a way we can compare one catalyst with the other. What we do is, in a flow system, flow oxygen 18 with propylene, then measure the 18-16 ratio in the products as a function in time. And what you essentially get then is treating this as essentially a dilution volume. You get a volume, a fictitious volume of catalyst oxygen participating. If we know what the stoichiometry of the catalyst is, we can compare that to the percent of the total oxygen that seems to be available for the reaction. Of course, you have to be worried about exchange reaction to study that. Again, this is just a summary. The key difference, again, between the molybdates and the antimonates is that the molybdates have very extensive participation of oxygen of the cell. In other words, there's high oxygen mobility. There's a tendency for many oxygen atoms to participate in the reaction. Antimonates, however, have very limited oxygen participation. In many ways, this looks like it's almost a monolayer, or a very thin layer. And ACS studies and other studies have tended to indicate that, in fact, that's true. The antimonates are highly enriched on the surface with antimony, and it's antimony layer that's really responsible for the reaction, whereas the molybdate is a much more broadly dispersed system where many oxygens participate in the reaction. Well, in terms of overall mechanism, Bob Russell and his co-workers at Ohio, I think, have put together a fairly straightforward, succinct mechanism that explains most of the observations that have been reported over the years about the oxidation of propylene to acrolein. They suggest that the pi allele is attached to molybdenum. The activation is by the bismuth oxygen. The question if this is bridged or double bonded is not terribly important. The key point here is that the bismuth site is responsible for activating the propylene to form a pi allele intermediate. The pi allele then can be converted to a sigma allele, which then, of course, it removes another hydrogen, forms acrolein, and you end up with a reduced form of the catalyst. Oxygen will reoxidize it back to the final state. Well, from this mechanism, there are several suggestions in terms of what we might be able to see by other techniques, such as infrared. Could we see the pi allele by infrared? Is that a signal, or is there something going on? Could we see the sigma allele by infrared, for example? What about the formation of carbonate species? So we've looked at, well, let me back up. Maybe I'll go to the infrared first. That's what we've looked at by infrared spectroscopy. What we've done is absorb propylene oxygen mixtures on these catalysts. This is at room temperature for short times, and you see nothing. And it takes at room temperature a long time for the development of these bands, but after about 1 day, you start seeing some band formation. And the 14, I can't see. This is the frequency associated with the pi allele. The sigma allele is 1606. I can't read that against reprint. So these two bands would be attributed to this pi and sigma allele species. And then as you start heating it up, you can start seeing the disappearance of the pi sigma, and we get the appearance of adsorbed acrolein. That's the 1686 peak. So we see the conversion of the pi and sigma alleles to adsorbed acrolein, and then at higher temperatures as we continue to heat, this band at 1615 is responsible, is And so you see the conversion of propylene to carbonate, which of course is the precursor to CO2 in water. Well, we've also looked at this using temperature programmed desorption, and it essentially agrees with what we've seen by isotopic tracer results with the infrared spectroscopy. Here, if we absorb propylene at about 100 degrees and do a temperature programmed desorption, we first see at about 160 degrees the desorption of reversibly bound propylene. At the same time, we see the production of water. Well, of course, if you remember the mechanism that I suggested for the Sohio workers, as you form the pi-Al-Lil intermediate, you would extract one hydrogen. There should be some water. So we interpret this water formation at about the same time propylene desorbs. Propylene to be desorbed, some of it will go on to the pi-Al-Lil, and you get some water formation at that point. I didn't point out, on the infrared spectra, we also see that at about the same temperature as this, about 150 degrees, when we heat to 150 degrees, we see the conversion of the pi sigma Al-Lils to the adsorbed propylene, to the adsorbed acrolein. So this is consistent with the idea that we're abstracting a hydrogen to form the pi Al-Lil. As we heat up, we see at around 210 the desorption of acrolein, and of course we see some more water coming off at that temperature. And that's also consistent with the idea that another hydrogen has to be removed in order to form acrolein. And so you see as the acrolein desorbs, you also see the desorption of the second water peak. And it isn't until fairly high temperatures that you see the CO2, which again is consistent with what we saw in infrared, that as the acrolein desorbs, some of it has a finite probability of reacting further with the catalyst oxygen to form strongly bound carbonate species. And as you get up to temperatures above 400 degrees, you start seeing the desorption of CO2. Well, this is our friend. And I think what I've tried to do today is try to show that the use of model reactions, as Keith has suggested, the use of isotopic tracers, the use of spectroscopy and other physical methods to provide complementary information about what you learn from the chemistry of the reaction is a very powerful tool for studying catalysis. And I am indebted for all he's taught me over these years, and it's been my real pleasure to be a colleague of Keith for so many years. And thanks to you, Keith, and thanks to the rest of you.
I just have a comment. Certainly enjoyed your talk, and I think you have provided now spectroscopic evidence for our mechanism. So, and I think that it is, of course, different from the one that Adams and Jennings proposed, where the second hydrogen abstraction preceded the oxygen insertion. And so I think you have now spectroscopic evidence that adds to the validity of our mechanism, which we have based on model compounds. Thank you.
Thank you.
Well, the next speaker will be Keith Hall, and we're going to finally learn about the relationship between surface chemistry and catalysis. Hall, and we're going to finally learn about the relationship between surface chemistry and catalysis. I am not going to give an introduction. I've asked George to give him a brief introduction because the only thing that I know about Keith are good. You'll used to give a talk, that's all you can say. So I'll turn it over to George.
Can't get up here yet, Keith. Somebody's going to have to put Keith's slides back up on the tray. I think Keith's got your slides in that other tray on it. It's on the floor. really doesn't need an introduction, but I guess I feel this is an honor and a pleasure actually to have the opportunity to introduce Keith to you. I think most of you know that Keith is a well-known member of the scientific community, and he's well known for his many important and continuing contributions to the catalytic literature. Even though Bob indicated that he wasn't sure if Keith was always somebody that, in the petroleum, one of the petroleum chemistry people, Keith really has spent much of his career working with the petroleum industry, first as a senior fellow in charge of the fundamental catalytic research for Gulf Oil's program at Mellon Institute. And then, of course, Keith went on to Gulf Oil's research and development company as a senior scientist. Actually, somebody was saying, oh, Dave, it's Keith's second career. Actually, this is Keith's third career. Keith was at Gulf, Mellon Institute, University of Wisconsin-Milwaukee, and now back to the University of Pittsburgh. In 1974, Keith received the Kendall Award based on the work that he had done at Mellon Institute with Gulf Research and Development. And I guess I'd like to think that the award he's received today has been based on the work he's been doing for the last 12 or 13 years at the University of Wisconsin-Milwaukee. In 1973, I was fortunate to convince Keith to leave Pittsburgh and come to Milwaukee as a distinguished professor of chemistry. Unfortunately for us, Keith is elected to take early retirement from UWM and return to Pittsburgh, where he's currently a distinguished research professor, and he's distinguished professor emeritus at UWM. During Keith's 13 years with us at the University of Wisconsin-Milwaukee, he established, I think, one of the world's leading centers for catalytic research. He provided training for over 30 postdoctoral fellows, as far as I can tell from Tom. He served as major professors for over 10 doctoral master's students himself. As I indicated, he served very frequently on committees for most of the rest of us who work with catalysis and surface science. While at the University of Wisconsin-Milwaukee, he published over 50 papers in peer-reviewed journals, and he received over $1 million in outside support to support his research. Keith is well respected by all of us, as evidenced by the fact that he's presented invited lectures, plenary lectures, several times a year, every year since he's been at the university, and as far as I know, as long as I've known him. He's been chairman of the Colloid and Surface Chemistry Division of the American Chemical Society. He's been selected as a featured speaker 5 times at Garden Research Conferences. To be invited once or twice as a featured speaker is unusual, but I think to be invited 5 times is indeed rare. Keith has received many significant awards. In addition to the Kendall Award, he received the Milwaukee section of the ACS Award in 1984. Just this November, he received the Pittsburgh section award. He's received 3 honorary degrees. He served as a member of the PRF Advisory Board and is currently a member of the Board of Trustees of the Gordon Research Conferences. As we all know, he's editor of the journal Catalysis, and he served as president of the Catalysis Society of North America. His international reputation is attested to by his selection as a 1984 recipient of an Alexander von Humboldt U.S. Senior Scientist Award, by his selection as one of the project directors in the U.S.-Soviet collaborative program in chemical catalysis, and by his numerous invitations to present lectures at many foreign universities and at a variety of conferences and international workshops. So it gives me a good deal of personal pleasure to introduce to you a close and dear personal friend, W. Keith Hall.